Hello and welcome to our presentation. My name is Helena Jarvis and this is Mary Skoudas. And today we're going to be presenting our research when we analyse planetary nebulae and the location of their turning points.
The James Webb Space Telescope aims to help NASA in its mission of uncovering the secrets of the universe. It's set to launch in October 2021 and thus needs objects in space to explore and analyse further with this new technology. Through the IRIS Cosmic Mining Project, we received data from an old space telescope, the Spectra Space Telescope, and analysed data from it to classify different types of stellar object and help identify these points of interest for the James Webb Space Telescope. Our aims for the project were to secure and apply an understanding of stellar physics, including spectroscopy, help astronomers identify these points of interest for the James Webb Space Telescope, and research further into planetary nebulae, their spectra, and how they can vary. So these are two spectra, and this is the information that received from the Spitzer Space Telescope. Spectra tell us the flux density of light, or the brightness, emitted by an object at varying wavelengths, usually between 5 and 35 microns. In order to classify them into objects, we split them into two components. Their continuum, that's the general shape of the spectra, whether it's rising, falling, has a peak or turnover point, and then features, and these are deviations thereof, so any bumps or spikes that we may see that lie outside the line of the spectra. And this can tell us information about any atoms, ions, or molecules found in the object. For planetary nebulae in particular, we were looking for a rising continuum, no stellar component, so that's low on the left-hand side of the graph, strong red excess, so high on the right-hand side of the graph, atomic emission features, so these are the successive spikes that we see on the left-hand spectra, and a continuum that flattens or dips at roughly 25 microns. And we call this a turnover point, but these can vary between planetary nebulae, so we decided to research it further.
This leads on to the two main reasons why we decided to focus our research on planetary nebulae. The first is the variation in the turning points. Some of the planetary nebulae had turning points at 20 microns, whereas others had turning points at 35 microns, and we wanted to find out why this was. The second reason is because there was confusion between oxygen-rich evolved stars and planetary nebulae, so we wanted to try and work out the key points as to why these are confused to help other groups in the future. We classified 14 planetary nebulae, which we understand is a small data set. Had we had more time, we would have classified more, and therefore this would have increased our accuracy. As you can see from the pie chart on the right-hand side, more than 50% of the classifications we made were using the high-resolution spectra. This was because the majority of the low-resolution spectra were cut off at 12 microns, and to locate the turning point, we needed to see up to 30 microns. And using different instruments, which is what the high-res does, allowed us to do this. You can see an example of a high-resolution spectra at the bottom of the screen. As you can see from the pie chart on the left-hand side, the majority of our classifications found that the planetary nebulae had turning points between 20 and 25 microns, and the smallest group had turning points at around 30 and above microns.
So then we began to ask why they had these different turning points. The peak on a spectra can tell us about the temperature of an object. As an object gets hotter, the wavelengths of light it releases move towards the shorter wavelengths, and we see this in our everyday lives. If you turn on the grill, it will release infrared radiation, and this will heat up your food. As the grill gets hotter, those wavelengths will move to the shorter wavelengths, and if the grill gets hot enough, move into visible light, and this is why we see it glowing red hot. So those planetary nebulae with peaks at 20 to 22 microns are likely to be hotter than those with peaks at 31 plus microns. And this can tell us information about both the age and the density of planetary nebulae. As they mature, they form areas of density. These areas of density have gravity, so material outside of them have a gravitational attraction towards them. The gravitational potential energy felt by these particles is converted into kinetic energy as it moves towards the area of density, and thermal energy through collisions. So planetary nebulae that are older and more dense and have had more time to collect this material are likely to be hotter, and therefore will have peaks at their shorter wavelengths.
As we mentioned previously, when making group classifications with our data sets, there was confusion between oxygen-rich evolved stars and planetary nebulae. IRIS are interested in oxygen-rich evolved stars without a stellar component because they could indicate the presence of precious gems. Planetary nebulae could have a broad emission or absorption feature at 8, 10, 18, 23, 28, or 33 microns, which indicates silicates are present. This includes silicon and oxygen, which we're looking for in an oxygen-rich evolved star. It could also have a broad emission or absorption feature at 30 microns, which indicates aluminates present. This is aluminium and oxygen, which is also found in an oxygen-rich evolved star. As you can see from the example on the board, it has a broad emission feature at 10 and 18 microns, as well as a broad absorption feature at 13 microns. It also has an early turnover point compared to most of the planetary nebulae we were classifying. So you may ask, why did we classify this as a planetary nebula and not an oxygen-rich evolved star? We classified this as a planetary nebula because atomic emission lines were present, and there is a strong red excess, which is not found in an oxygen-rich evolved star.
Throughout our project, as a group, we've all managed to further our ability to classify objects and further our understanding of components of stellar physics we previously had no knowledge on. We hope that along with schools across the country, we've been able to positively contribute to the James Webb Space Telescope's mission. Of course, we had limitations to our research. The small data set of 14 planetary nebulae are unlikely to be representative of planetary nebulae as a whole, so it's difficult to draw conclusions from them. And the use of both the high and the low res spectra may have impacted our accuracy. Given more time, we'll classify more planetary nebulae in order to learn more about their turning points and research further into the information turning points can give us about how planetary nebulae mature. We hope to share our research on how O-rich evolved stars can be confused with planetary nebulae with future groups completing this project.
We thank you for listening to our presentation and welcome any questions you may have.